Today I'm going to just do a lab with several switches connected together as shown in this PowerPoint here. Basically showing off spanning tree protocol. I don't really have a lot of understanding about how spanning tree works behind the scenes. I know what it is. I know it puts one of the ports in blocking so that way traffic just doesn't keep going around and around. But I don't really know how it works exactly, so I've got several switches set up here, and I'm just going to play around and develop a little bit of better understanding of spanning tree right now. So we've got these top two switches are Cisco Catalyst 2950s, and the bottom two are Cisco 3560s, I believe. We have a crossover cable connected between these two because otherwise they don't come up. And these are all straight through cables here, here, and here. The labels show which ports are connected, and we're gonna just look at it. Now my first understanding is in spanning tree, the lowest MAC address determines the root ID, or the root bridge. Well, priority wins first, but then after priority comes the MAC address. So we want to figure out which one of these switches has what MAC address, and I'm going to just find out and label them here. We can find the MAC address out in the output of show version, just looking for the MAC field. So those are all of our MACs, and I'm going to put these in the table over here. The program I use here, so I can easily split one terminal window into multiple parts, is called Terminator. It's a Linux program. I'm not sure if it runs on any other platform, but I kind of like it a lot for running multiple windows like this. It takes up less screen and real estate space than actually having 4 instances of the XFCE's terminal emulator open. So change the font size, that's a little bit too big. So these are all of our switches and their MAC addresses. And since they should all have the same priority, the lowest MAC address should be our root bridge. So looking through all of these, it looks like the lowest MAC would be this one here. So this here should be our root ID, our root bridge. So that would be this one here. So let's see here. So spanning tree. Now I think default it uses per VLAN spanning tree. So each one has its own instance. So let's see here. The root ID is this one here, 04CO. Is that what we said? Yeah, 04CO. And the priority of, is usually defaults at 32.768, and it has to be in multiples of 4096 because it kind of gets added, the VLAN gets added to the priority value. So we see this is 32.769. This bridge here is the root, and so that means the other bridges are not the root. Now since this bridge is the root, these should be forwarding here, and I think they're called designated ports. And then on each switch, the path that it uses to get back to the root is a root port. So let's see here. Yeah, so these are designated ports here. So let's see here. And this FAO1 is a root port to get back. And on this one, FAO2 is the root port to get back. So that would mean that, okay, that these are the designated ports, these are root ports, and these were also considered designated ports as well. So the question here is which one of these blocks, and let's see if okay, so so this is a root port, and this is an alternate port. I think this is on per VLAN spanning tree. So let me see here. What's the spanning tree mode? See what the configuration says. Yeah, it's on per VLAN spanning tree, not rapid spanning tree. So let me see if I can find out what that means exactly. Okay, so it looks like it means it's some alternate port, and it blocks, basically. Traffic doesn't go through those, which it says right here, blocking. So how does it come to the conclusion to block this one and not this one? I mean, we have equal cost this way, and we have equal cost this way. So I think the next consideration is the bridge priority. I mean, of the sender. And so this guy has a sender of 0D, and this guy has a sending priority of 1.9. So I think that's why this item gets chosen as the root bridge, because it has the lower priority. But if we boost that priority, then that should change, I think. Let's see. And there I am forgetting my own thing that I just said, that it has to be a multiple of that. Okay, so changing that did reset it, but since I lowered its priority, it should still be the Okay, lowering that priority made that the root bridge. So now with this the root bridge, these would be forwarding. This here would have to pick the lowest cost. To determine which to block, and I think this one would be blocking. No, this one would be forwarding, this one would be blocking on F01. So when I changed the priority of this bridge, it became the root. And then this bridge and this bridge both have a root ports going back here with a cost of 19. So these have paths back with a cost of 39. And since they both have equal costs, it would choose the sending bridge with the lowest bridge ID, which would be this one here. So this one is forwarding and this one is blocking. Now we can change the cost of the port independently for it to pick this path instead. And the cost is calculated at the destination switch, not at the source switch. So we'd have to change the cost on this one here. So by making this cost higher, it should now prefer this way, and this one would go into blocking. So I wonder what happened to... Okay, so... So the port that blocks is determined first based on the shortest cost of the root bridge, but then after that the shortest cost is the bridge ID. So I wonder what would happen if we had two connections, say between these two. Say we also decided to add F03. So we already know that this guy is the root bridge right now. I'm not sure why it's doing that, but so if this guy is going to be the root bridge, then traffic will have to go either this way or this way through him. But if we remove this link, I want to see which one of these ports becomes blocking versus non-blocking, because we're going to be receiving the same cost over both of these links, and it's also going to be coming from the same sender bridge. So I think the next thing is the bridge priority, or the priority of the port number. So we can see that faster than 03 just came up on each of those. Okay, we can see on this side, both 1 and 3 are designated ports, and on this side, 1 and 3 is either a root port or an alternating port. So O2 is already being blocked, so this is being blocked, and O1 is forwarding, but O3 is blocked. I think this one has to do with the priority of the sending port. This is blocking because the sending port over here I may have a bad cable there. But the sending port over here has a lower priority and therefore takes precedence and becomes root. So let's test that here. So that's a 128, so let's make this one 129. And look, see there's. Alright, so it does look like it's the sending priority that determines which link is active. because we just saw these swapped up here. F1 was the root port, while this F03 was blocking. But down here, Fast Ethernet 01 is blocking and Fast Ethernet 03 is sending. So looks like what happens when you have two links between them. The sending port with the lowest port priority is the one that stays active, while the higher port priority would be put into blocking state. So what happens if one of these guys is the root bridge? Okay, so it seems like what happens is, first of all, the root bridge is determined based on its bridge ID or its priority, where the lowest priority wins. If there's a match in priority, then the bridge MAC address is used, and that becomes a root bridge. And all of the ports on the root bridge stay open. Now, any port that's connected to a root port, or to a designated port, is a root port. So this would be a designated port here. So these would be root ports. A root port on any given switch is the port that has the shortest path back to the root bridge. Now for each switch, it might receive multiple paths back to the root bridge. So first it picks based on the cost, and then if you have the same cost, such as if you were here and you were receiving the same cost to the root bridge this way and the same cost to the root bridge this way, the next tiebreaker would be the advertising switch's bridge ID. The lower bridge ID would win. And if they happen to be coming from the same bridge, like if we had two links between here, then the lowest sending port priority seems to win. Now, it seems like when you have two links and you have one side that might be blocking and one side that's not blocking, you have to determine which one will block. So why is it, for example, this one blocks and this one is forwarding instead of this one blocking and this one is forwarding? And it seems like because the reason they don't block both ports is because you may have like a hub or a switch on here, a hub or something, that could have more traffic. So even though it looks like point to point, you could actually have another network segment here that's not participating in spanning tree. You could have a hub here, and you could connect several devices off of that hub. So one of those two ports has to go active to still forward traffic. So I think it's still a cost thing. So if this was the root bridge, then this guy would have a shorter cost than this guy would have to get to it. But if we had a direct connection between the two, so this guy would have a cost here, and this guy would have a cost here, it would probably go by the bridge ID. This would have a lower bridge ID, so this would become the root port, and the one on this side would become the blocking port. Let me find out though. I'm going to connect F04 from here to here and disconnect these two. We're going to keep this guy as the root bridge here. Okay, so now we have this guy as the root, and this guy have an equal cost to the root. There's a link between each other. So the question now becomes which side of that link becomes forwarding and which side of that link becomes blocking. And I think I may have unplugged the wrong cable here. So now we've removed this link here and instead connected 4 to 4 here. This link's still here, this link's still here, and we still have 2 here. And so this switch is the one that's deciding to forward. Through here and here. So we have a cost issue here, that's why. Turns out one of my cables was bad. So on the root switch, both of the interfaces are the designated. And this one here has a cost of 19 to get to the root. This one has a cost of 38 to get to the root. I think we plugged that in wrong. So many cables, it's kind of hard to tell what's being plugged into what sometimes. Okay, so now we see we have a cost of 19 to get to the root bridge here, and a cost of 19 to get to the root bridge here. It's saying the root bridge is on Fast Ethernet 4, which is right. And on this one, it's out Fast Ethernet 2, which is right, because this is Fast Ethernet 2 here and Fast Ethernet 4 here. So between the links between here, I'm interested in knowing which one goes designated or which one goes blocking. So on this one, port 2 is still linking up to switch 2 here, which we can see. We've got a cost of 38. Now, this shows you that the cost value is local, because even though we have a cost of 20 here, as far as this guy's concerned, we only have a distance of 38 instead of 39, because we have 19 from here to here. This guy receives it on Fast Ethernet 04, and then this guy receives it and adds his 19 as well. Even though it's going out 20, it doesn't get added on its way out, it gets added here when it's received. So why did this side choose to block and this side choose to be the designated path? If we look at the bridge IDs here, this guy is 1.3, this guy is 1.9. So my guess would be, once it determines, okay, both sides have the same path to the root bridge, perhaps the one that stays open is the one with the lower bridge ID. And I sense priority is counted into that. Let's see here. It's OD. So if we put these in the same priority, this should still be the root. So I'm going to guess that even if we change the priority, that between these two, which one goes blocking and which one goes forwarding is probably only determined by the bridge ID and not by the priority value. Actually, this had a lower priority, so this would have been forwarding anyway. So let's see here. It actually seems like the priority is considered part of it, because now this side is blocking and this side is forwarding instead. So aside from your root port, you can generally have two different types of links between the switches and spanning tree. You can have it where one side is the designated port and one side is a root port, and the root port's the shortest path back, and the designated port is the way that the other switch gets back. Or you can have it where one side is a designated port and the other side is blocked, and that occurs if the switch has its own shorter way back. For example, in this case here we have two switches, but this switch's shortest path back is through a different switch than this switch's shortest path back. So it would not go through here. So one of these would block and one of these would be forwarding, just to have any other possible networks on this segment or other devices that might be connected on this segment to be able to be part of the traffic. And the way that decision is made is whichever one seems to have, first of all, I think it's the lowest cost, and then after that it would be the lowest bridge ID. And we didn't really see cost here because the other situation that we had, one of these was going through here. We could see cost by tweaking the port. So right now this side is blocking on 01 and 03, but forwarding on this side. But if we change this cost to be a little bit lower, then the link between these two would say that this bridge has a lower cost back to the root, and so it should go forwarding instead. So my prediction is this side should start forwarding on FO1 and this side would block. But for this link between the two, I think it would stay the same. This side would block and this side would forward, because this guy's technically has a lower priority right now. I could be wrong. And it looks like I am wrong. Let's see what happens if we set the priority back to normal here. Now this one should start forwarding because it has the lower bridge ID, and then these would go blocking. Okay, maybe not then. So it looks like when it comes to the segment between these two switches, where one side's going this way and one side has the route path going this way, when it determines which port blocks or which port's open, it doesn't look like the port cost is taken into consideration, only the bridge ID. Because anything on this segment would have a cost of... Oh, actually it's coming in from FO2 here, isn't it? So it would probably depend on this cost here and not the cost between the two. So let's lower this cost instead of those costs, perhaps. Because as far as this switch is concerned, 18 is the shorter cost. And I suppose that would make sense because the cost doesn't get added until it gets to the other side anyways. So as far as this switch is concerned, its cost to the switch is 19, and its path is also 19. So anything that's just on the segment here sitting would only use this 19 or this 19. It wouldn't add the segment itself. Maybe. And we see it did change here from forwarding on this side to blocking on this side, because any segment that's here, the cost from here to the root is 20, while the cost from here to the root is 19. So this side's blocking and this side's forwarding. So anything that was here transmitting traffic out a hub, it would go both ways. But this side would just discard it, and this side would forward it through to the root, which could then forward it either to this switch here. Well, actually this link is down, so it would go this way to get to the root, or it could go this way Of course, the MAC address is going to be learned in all the switches. So really, the spanning tree is only for broadcasts. That gets sent out all ports to control that. So the MAC address is learned from here to here. It's not going to send it to the root, it's just going to send it straight here. But anything that does have to go somewhere and it doesn't know, it would forward it here, and then it would flood it here and to here, and this device would flood it here if it was a broadcast frame.